files and throwing them on YouTube sometimes is not possible. Yes, Reem. Yes, please switch the AC, switch off the AC here first. Okay, so Reem's requests are never... Okay, so you tell me, any feedback about lab 1? Anybody has difficulty? All is well? Shall we directly start lab 2?
Doctor, are we gonna go to the lab?
Excellent question, Antonio. Thank you so much for this question. Listen up. So far, I've been receiving emails from the provost and then from the department that they want to try something specially for the lab. Okay. Also, they said that this thing is not, it's optional for the students. Like, if you will end up coming to the lab, it's gonna be like, if you want to come, you would come. Otherwise, you will keep doing the online thing. But I don't know how it's gonna be optional, and I don't know how what is the procedure for the precautions. Like, they're still working on creating a procedure on what to do, the number of students, and so on and so forth. What I'm trying to say here is that nothing is final yet. But what I love us to do is to try to have the midterm on campus, because I don't want you to struggle with the midterm online. And I love to have your midterm being on your laptops, like computer-based. How do you feel about it, by the way? How do you feel about having your midterm computer-based? Like, you do it in a room on campus, and I will be there to proctor you and maybe answer some questions, but you will do it on your laptop, meaning you do the calculations, the plots on Excel. How do you feel about it? And eventually you submit a file online, as compared to being paper-based. All right.
We don't know how to use Excel.
Okay. Anyway, lab 1, 2, 3, 4. Yeah, 1, 2, 3, 4 are gonna be online, right? So you are doing all the calculations on a file. You will have Excel soon. Lab number 3, if I'm not mistaken, will be full with Excel, and I'm gonna give you a session, a live session about it. I mean Excel, how to plot and find the slope, you know, and we already did that in lab 0, didn't we? Maybe you're not experts yet, but I believe doing it on Excel is much easier and faster than doing it on a graph paper. And doing linear regression to find the slope on Excel is much easier than doing it on a calculator, you know? And since you're training yourself to do it on a computer, why go back to the paper and do it on a calculator? I don't see the point. So, but I do understand your fears, and since the point of the midterm is not to stress you out, is only to assess what you know, so I will definitely ask you about it when you are close to the midterm. So the midterm is happening around lab 5, which means in 3 or 4 weeks or 1 month from now. So until then, I think maybe you will have a different opinion. Okay, but I will ask you again. All right, so I don't know yet anything about campus or not. Believe that you will always have the choice. And I want you to trust the fact that I will definitely share anything that comes from my side, okay? Like, if the department will share anything with me, I will let you know immediately, okay? All right, so lab 2, equipotential lines and electric field mapping. Let me start by asking you, what is a field? How do you define a field? Can you give me an example of a field? Try to speak up. Okay, before you talk, let me quickly...
Electric field.
Electric field. Let me just check your names, because I would be happy to talk to my audience. Just give me a second, so I can move it aside. So the point of me calling your name is only to interact with you. So Ratib is saying spectrum. I like this one.
It's a region surrounding charged object.
Okay, I like the fact that you're saying it's a region. So a field for you is a space, a region. You said electric field. Ratib talked about spectrum. Spectrum is not clear to me though, if you can explain. Can you also give me other examples of fields?
Magnetic field.
Magnetic field. Any other
I guess,
field?
I guess in a sense, gravity is a field as well. It's not in the way we can, not like the others, I guess.
It's exactly like the others. Why do you think gravity is different?
I think because like some people say that, I don't know, I'm not too knowledgeable about this, but it's like there's a the presentation of it is different. It's presented as like a third or a fourth dimension.
Okay.
I think the experiment with the cloth and the balls that represent the planets, for example.
Yeah, you're talking about the a twisted 3D space due to gravity. Example, so Latif is saying filled with components that are related to the environment. Example in our, okay, I can see what you mean. All right, so you guys, for me, the three different fields that we can name, the electric field, the magnetic field, and the gravitational field, are all fields, all right? They are similar on so many levels and different on some levels. For me, us humans are experts in gravitational field because we experiment gravitational field every single day. Since you were born, you were 8 months old, you were actually throwing your spaghetti on the floor, your mom used to go crazy, you were basically experimenting gravitational field. So you know a lot about it. A field, I cannot smell it, I cannot touch it, I cannot see it. How do I know it exists? Like here in this room right now, is there any gravitational field? How do I
can see
know?
its effects.
The effects.
The effects
Yes.
of it. Okay. Can you explain or give an example?
Yes, for example, the electric field, you can't see it, but you can put test charge and you see the effect on this test charge, so you can know what the field acts on.
Thank you so much, Rudy. So you can easily test the field. A test charge would tell you if there's an electric field. A test mass will tell you if there's a gravitational field. All right, now in the next slide, I want to show you some differences between gravitational field and electric field. You can see that for the gravitational field, it's always radial and pointing inward towards the source of the field. For the electric field, it is radial, but sometimes pointing outward and sometimes pointing inward, depending on the nature of the source, if it's positive or negative. Also, you can see that both fields are proportional to 1 over d squared, the distance away from the source, and the test mass or the test charge would feel a force parallel to the field or opposite to the field, depending if the Q is positive or negative, but the behavior is basically the same. We don't have negative masses around us, otherwise maybe we would had, I don't know, maybe electric fields pointing outwards. All right, now the question in this slide is the following. Can you tell me in which, by the way, question number 1, the sources A, B, and C do you think they're positive sources or negative sources? And these are
Positive.
Positive because?
Positive.
The lines outward.
Because the electric field lines are outward. Can you tell me which source is stronger or the strongest?
C.
Because?
The field are larger. Large field.
How do you know the field is larger? I don't see values.
No, there are
Number of lines. Number of lines.
Yes, I can hear you. So the density of lines is very important. It's proportional to the strength of the source. So the stronger the source, or the stronger the field, the more lines you're gonna draw. In few minutes for this lab, we're gonna draw a map, and the density is gonna be very important. So take it from me, density is high when the field is strong, okay? So I don't know if we can underline it. So when the density is high, the quantity, okay, so the density is proportional to the quantity of charge, okay? That was a very thin pen. I know you know this from grade 11. This is basically review. So as you can see, this is grade 11 material. Remove the pen. Now this case, you have two sources facing each other, both of which are equal in magnitude and both are positive. Can you compare these two sources? It says here, yeah, you want to say something?
It's dipole, I think.
You can say it's a dipole, and by dipole means you have two charges of opposite charge.
Yes.
Okay.
The number of lines that goes out from the positive one is the same number as the ones who arrive at the negative one.
Thank you, Rudy. You answered my question that I did not ask yet. I wanted to ask, how do we know that these two are equal in magnitude? Because the number of lines is equal, like the one coming to this one is equal to the one going out of this one. By the way, what do you see in this figure? Do you see E1 or E2? What these electric field lines?
The resultant, I
It's
guess.
the resultant. Yes, thank you so much. So no, Ratib, I know you meant something else. We don't see both, we see the resultant. So here I cannot see E1, I cannot see E2. I see the resultant of E2, and my resultant is the resultant vector. So if E1 and E2 are pointing opposite, equal and opposite, they cancel out. That's why you have 0 in the middle. And when you have a vertical upward electric field, it means the x components of the field will cancel out. Yes, so all these lines, Ratib, and everyone else are parallel to the resultant electric field. So in this case, there's no way I can measure E1, neither E2. What I see is the resultant. All right, now I'm gonna discuss some dynamics and some motion. Let's say I put a proton at point A, as stated in the question here. What do you think will happen? Yes, Hagab, I'm recording the session. So the question is, if I place at point A proton P, what do you think, how do you think the proton will be? A is attracted. Can you explain? Attracted to who? To the negative charge. So Ratib is saying that the proton is always attracted to the negative charge because unlike charges attract. So this is the reason why a proton would move from A to, let's say, O. If I put the proton at point B, it's gonna move from B to C. Some other students would say, all right, Joe, you're right, the proton in an atom will not be able to move because it's inside the nucleus. This is a single proton, free to move. Okay, so it's not inside an atom. All right, so yes, the proton would move. Any positive ion would move if you put it close to a negative charge, attraction would happen. Or you can simply say, you would feel a force, and let me write it down. Isn't the force on the proton equal to Q of the proton? I don't know if I'm lagging actually. You tell me. All right, so this is an F vector, so, and this is an E vector. So since Q is positive, F and E are pointing in the same direction. That's why P would move along the electric field line. And let me write it in here. So P moves along the electric field line. Another question. You just told me that B and C, the proton would move from B to C. Can you compare the potential of B to the potential of C? Which point has a greater potential?
C.
Okay, let me give you a hint. P moves from a high potential to low potential. Let me make this smaller, it's huge. Okay, so what happens if you put a proton at point A? P moves along the E, the electric field lines. P moves usually from high potential to low potential. So which point has a high potential and which point has a low potential? I'm comparing C to B.
B has high potential.
Exactly.
Yes.
Yeah, so P is a proton, and a proton is a positive charge. That's why it moves from high to low. If I'm talking about a negative ion, it's gonna move from low to high. So depending on the type of the test charge. All right, so can I say that there is a potential difference between B and C? So it is not equal to 0. Let me say it's not 0. Is that good? So the potential between B and C is not 0. Now I'm gonna show you another point that is like this. I'm gonna call it point D. Do you think the proton can move from B to D? Yes or no, and why? Why not? So B to D, motion would happen, yes or no? Anyone? Hatib is saying no. Can you tell why?
Maybe I think it's because two field lines cannot cross. Maybe.
All right. Definitely two field lines cannot cross, but we're talking about the motion between B and D. I can give you a hint. The motion is perpendicular to the field. So no motion. So no motion can happen perpendicular to the field. That's why no motion between B and D. Now my question is the potential of B versus potential of D. Can you compare? Which one has a greater potential, B or D? Equal. Thank you, Anthony. They have the same potential. Basically, for you to be able to increase the potential or decrease the potential, you need an electric field to be able to do so. Isn't potential the derivative or the integral of the electric field? Anyway, so if there's no electric field pointing from B to D, there's no change in potential. So I'm gonna say no potential difference. Can you tell me how I measure the potential difference in the lab? How do I measure the potential difference in the lab? Voltmeter, thank you so much. So I'm gonna say the voltage between, or let me call it simply voltage BD is equal to 0. Okay, so now I'm gonna draw this line that is perpendicular to all the electric field lines, and I'm gonna say the voltage between any 2 points that belong to this line will give me 0. And I want to call this line equipotential line. So do you understand what's an equipotential line? Who can give me the definition of an equipotential line? Can you try?
All the points on that line have the same potential.
Okay, all the points, they have the same potential. Maybe we can add that the equipotential line is always perpendicular to the electric field line. I can add that any 2 points on the equipotential line would give you a voltage equal to 0 or the difference to be equal to 0. So now you have many ways to find the equipotential line. So basically, in the lab, we cannot measure electric field. We only have a voltmeter. We need to find all the equipotential lines, draw them, then draw the electric field lines perpendicular to them. So for me to find, let's go back to the title, to see to do the electric field mapping or the map of the electric field, I want to draw all the equipotential lines first, then deduce the electric field lines to be able to create a map like this one. By the way, we're taking this example in the lab, so you know the answer, but your job is to learn how to build the map. Now let me show you some lines here and there. You see the blue lines are electric field lines, and the dotted black lines are equipotential lines. So you see they're always perpendicular to the blue lines. Yes, this is the case we're gonna have. So you can expect, you know, from now what your answer would be. Your equipotential lines would be straight in the middle, then they will curve as you get close to the charge. Let me zoom in. So straight in the middle, and they will curve as you go close to the line. If you measure the voltage between this point and this point, what do you get?
0.
0. And if you measure the voltage between this point and this point, what do you get?
I guess the opposite.
Not 0. All right, you mean the opposite, exactly the opposite. Actually, I don't know, depending on the reference. So in the lab, you will be given a difference of 20 volts between these two. Difference of 20 volts will not tell me the potential of the first and the potential of the second. I only know the difference is 20. So it could be 0 and 20, or negative 10 and positive 10, you know? So I can never tell the potential unless I take a reference that is ground, which is 0. So you will put the reference of your voltmeter in the middle, and find all the points that would give you 0, and then you will draw this line. And then you will find another color, move your reference, and find all the points that will give you 0, and then draw the line. So I think, and I'm not sure, I'm gonna make your life easy. I think I'm gonna give you coordinates, and you will draw the lines to create your map. Maybe this will be easy for you. This is another example that will show you some equipotential lines of a random distribution of charge. You can see this one has a potential of 1 kilovolt with respect to this reference. So, and this one I think is 3 kilovolt. So you know the difference is gonna be 2 kilovolts. This is all you need to you know how to measure. So if you ever know where is the potential 0 or where is ground or where's your reference, you can tell exactly the potential. Otherwise, it's gonna be potential difference only. All right, are you ready to show you the equipment? I'm gonna put this away and go find the video. All right, in this video, I would say that this is a Physics 306. Forgive me for this one. So it is for your class, don't be confused. Will I be able to see the chats? I'm gonna put the chats back here. Don't worry, Ludovic. Hello everyone, welcome to the first experiment we have for Physics 306. So this is the second experiment for Physics 201L. I'm sorry for this confusion. Electric field mapping or equipotential lines, all right? So let me get the camera closer to show you the different equipment we have. All right, so the equipment needed, you need a multimeter. This is the test multimeter I will be using on the scale volts. You need 4 banana wires. So you can see 2 banana wires already attached to your power supply, and another 2 banana wires that I will be using for my multimeter. By the way, this is the power supply because you won't be able to see it. It's a DC power supply. You can control the current and the voltage as you may. You have the positive terminal and a negative terminal, the power on-off button, and it's connected to the mains. What else? This is a board. It's a board on which I'll be using a conductive paper. This conductive paper is supposed to be brand new, so it shouldn't be poked anywhere, and this is the case. So I'm gonna take the conductive paper. So that was the equipment needed. Now the procedure. I'm gonna place the conductive paper on top of the board. I need to make sure I have conductive pins attached to my wires. Okay. I'm gonna poke. By the way, this experiment has one of the most difficult procedures. Like usually I repeat it on every bench. That's why I'm maybe talking slowly. I want you to follow it well, because if you don't get the point, maybe you will be confused, but I think you will eventually get the point. The paper rigidly at the extremities of the paper. Okay, so you can see that I created 2 videos, just separated the video into 2. One pin is connected to the red banana wire that goes into the minus terminal, and one pin is connected. Listen, observe the video very well, because you may need to take some data out of it. For example, here, you need to know that where's the positive source, where's the negative source. In a few minutes, I will tell you the different coordinates, all right? Good, you can or cannot. If you cannot see it well, don't worry. I'm gonna share the videos with you. You can watch them later, okay? With any resolution you want. The blue banana wire that goes into the positive terminal. The power supply is off, so there's no potential difference between these 2 wires. But when I put the power supply on and I see a 20 volts displayed on the screen, I would know that I just created 2 point-like charges. The potential difference between these 2 point charges is 20 volts. And I can say one source is positive and one source is negative. So you know what to expect concerning the electric field. job is to use the voltmeter, the multimeter on volts, to be able to try to do some measurements. All right, I'm gonna show you one trial, at least, for you to understand how I'm gonna find those coordinates. I will use my voltmeter on the scale 20 volts, because 20 volts will give me 2 decimals. I will not be measuring voltages more than 20 volts, more than 2 volts though, so I can simply use 2 volts as well. But 3 decimals for me is a lot of precision, and I don't need this, knowing that the experiment is not super precise. So a scale of 20 volts or measurements of 2 decimals are enough. I'm gonna take these wires, the blue and the red one, plug them into the COM and the V plugs. And I'm gonna use, I will put this to the camera, hopefully you can see it. Okay, and I'm gonna be measuring the voltage or the potential difference across my paper. If I measure the pins, the potential difference across the pins, I should get something very close to 20, and I'm not, because my power supply is off. I will put my power supply on, and I can see a measurement very close to 19.9 volts, which makes sense because these are the terminals of my power supply. Now, if I measure the potential difference across 2 different points on the paper, I can see that it's a non-zero measurement, which means these 2 points do not belong to the same equipotential lines. Remember, points do belong to the same equipotential lines in case they have the same potential, therefore the potential difference is 0. Now my job is to find equipotential lines and to be able to map them. So I'm supposed to find 2 points or many points belonging to the same equipotential line, therefore having the same potential, therefore having a potential difference equal to 0. I'm going to start with my red terminal being my reference exactly in the middle of the paper, and I'm going to try this point. Does it give me 0? No. I will move it a little bit to the left to get 0. I found my 0. I write down the coordinates of this point. I'm going to move now the blue terminal 1 centimeter up. Is it a 0? No. I will move it a little bit to the left. Bingo, I got 0. I will mark my coordinates. And so on and so forth. I'm gonna find all the zeros, mark them. I don't know if you saw that the red wire is not being moved. I'm only moving the blue wire. Or at least one, like the voltmeter has 2 terminals. I will fix one to be my reference, and I would use the other one to be able to find the different zeros. And usually I move 1 box to, like upward, find the 0 right and left, then 1 box upward, find the 0 right and left. I don't know, in some other procedures, maybe other sections of Physics 201, they're not doing that. They're not finding the zeros. They're finding a potential difference equal to 2. And they're putting the reference on one of the sources, like they put the reference on the sources, and they find the potential that is 2, potential that is 3, potential that is 4, you know? That's very difficult because it's very difficult to hit 2. It's so much easier to find the zeros. So I'm gonna make sure my procedure is very similar to the procedure in the manual. Otherwise, I'm gonna change your manual to make it less confusing. Ratib is asking, the conducting paper is creating the electric field, right? No, what's creating the electric field is the following. You have a point-like source here that is red, and another point-like source here that is blue. The blue is connected to the positive terminal of the power supply, and the red is connected to the negative terminal of the power supply. A power supply is like a very big battery, so it creates a potential difference that is constant, and that is equal to positive 20 volts. And in other words, I have a positive or a negative source, and then a positive source, and what I have in between is the electric field lines. So who creates the electric field lines? It's the 2 sources connected to the power supply. The paper itself is only a good conductor, all right? Otherwise, it will be an insulator and you will have no electric field in between. Hagop is asking, when you are speaking, I can imagine the lab video. Okay, that's great. I hope when we will be back to the lab, you can try for yourself because it makes a huge difference. Joe, if we take another origin for the red wire, the blue wire have an electric field 0 only in the right and left. I cannot understand the sentence. If we take another origin for the red wire, I have an electric field 0. So you mean if I move the reference, yes, I will be drawing another line, you know? All right, so basically, I will put the reference in the middle. I will find the first equipotential line. Then move 1 centimeter to the left. This is another line, maybe with another color. Then move the reference to the left. This is another line, another color, you know? So every time I change the position of the reference, I will have a new equipotential line. All right?
Miss, it's not so practical, right? Because you have to do it for every line, and every line has a different curve, so it takes time.
Exactly. Usually, we ask the students to do the map for every single point, like 1 centimeter at a time as you go up, 1 centimeter as you go down, 1 centimeter as you go right, 1 centimeter as you go left, and usually it takes them 1 hour to finish, only the map. So you're lucky I'm doing the map for you, and you're lucky you're not required to do all the lines. You will be given maybe 5 lines, not more. So just imagine how the map will gonna look like. But again, Joe was talking to me, I can't remember. So again, it's not as difficult as you think. Yeah, Rudy, it's not as difficult as you think because you will not be required to write the coordinates. Please mute yourself. I can hear myself. Yes, so you will not. Please mute, Rudy. Okay, you will not be required to write the coordinates. You will simply move it quickly, tack, 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 and you will tell your partner, move up, move up, move up, move up, move left, half a box, you know? And you're not supposed to be super precise because if you zoom into the conductive paper, the smallest subdivision is 1 centimeter. It's huge. So you can tell your partner, move half a box. You cannot say quarter of a box. So it is really fast. Maybe the first 3 lines will take you 10 minutes, but then you will be quick. Like move right, left, 1 box, half a box. You don't give coordinates. Coordinates usually are so time consuming because you need to translate a point into coordinates and then translate coordinates into a point on your paper. And by the way, students do not draw on this paper. They create another paper that is from a notebook. And then you can see the points 0 to 20 and then 0 to 28, if I'm not mistaken. And you will put the points on another paper, not on this one. So usually you should be 2 students to be able to do this lab, a minimum of 2 students. One would deal with the voltmeter and the other one will quickly draw the equipotential lines on a different paper. All right? So I'm not gonna continue the video, but you are required to watch it again. Pause as much as you want and play as much as you want. Let me show you the lab report before I leave you, because maybe I can see how it looks like. I'm gonna modify it a bit before sending it to you. Let me see what I have. Okay, there's a manual part and a report part, but I'm gonna send you one combined. By the way, I usually send you a PDF version and a doc version. I always believe PDF is good for you if you want to view it from a tablet. And I always believed a doc version is good if you want to write on it and modify. So it's up to you. Check what you want. This is the, all right, did I open, how many files? Okay, many windows. Okay, let me check the manual first. The reason why I did not send you the whole manual is because I would love to do some modifications on each. So equipotential lines, they explain a little bit theory, procedure, equipment, objective, procedure one by one. Let me read it first. I would love to modify a bit on it to make it easy and maybe more informative. Concerning the lab report, you will be given some coordinates. I will fill this table for you. You see 5 lines. Maybe I can give you 3 results and you pick one. Like I give you 3 different tables and you pick one for you not to have similar lab reports. Describe and explain what you observe in the graph. Is it possible? Like all these questions are descriptive. Sketch. What do you believe? What maybe I will add some questions and remove some, and maybe this one is not very clear. I'm gonna change it a bit. Okay, so that's it. You see? So a very simple lab report, but a bit confusing. All right, do you feel ready to present this lab report? So I assume you're gonna type your answers inside. If you want to sketch, you can simply do it on a paper, take a picture with your phone and insert the picture in the document. Make sure you give me, please send me the lab report only. So start from here, title, your name, the date, and fill in this, answer the questions in the blank, everything typed, or a picture, insert picture or graph if needed, and save it well. You can save as PDF if you want to make sure everything will not move or will not get modified. And let me see it submitted on Blackboard. I'm gonna start correcting your lab 1 this week. I will give you feedback about your presentation, okay, under announcement, like if there's something you need to change. Where is the graph? I'm gonna give you this table full with coordinates and you will do the graph. And when they ask you plot the 5 equipotential lines on a graph, you have 2 choices. You either do it on a graph paper, Joe, take a picture, insert in your lab report, or you can try on Excel. Let me show you how I do it on Excel. How come Excel is not opened? Usually I use it every day. I think I closed Excel a few minutes ago. Okay, this is Excel. Okay, let me show you a simple way on how to create a graph. Maybe you know already. So I start with X, then Y. Let me make it bigger. So random values, 1, 2, 3, and 4. And this is 10, 20, 30, 40. Okay, so basically you're gonna show X and Y, but in your case you have many X and Y, like 5 different lines. You select only the values and you say insert, and you see the scatter, you pick. In your case, for the map, maybe this one is gonna be nice. Usually we pick the scatter that is empty to do the slope and the linear regression. But here we're doing a map, so maybe this one would look nice. Okay, in your case, you're gonna have straight lines. Now you need to learn what happens if I show many X and Y. Do you think it's gonna work? Okay, usually what I do, I add sources. So how about I give you time to think for yourself, how can I create 2 plots on 1 plot? It's very easy, just find it on YouTube. And if you don't know how to do it, you're stuck, let me know. I will give you a few days to figure it out. You tell me, I can create a video to explain it. Otherwise, just do it on a graph paper and take a picture, okay? This is not important. It's a map eventually. It's not a graph that I need to do data analysis, right? So that's it. Any other questions? So again, remember, during the coming weeks, you will learn some skills under writing a lab report. So every time I see you're missing something about the font, something about the font size, something about the presentation, and this is not graded, by the way, I will let you know, because eventually by the end of the semester, I want your lab reports to look nice and professional and, you know, to have an official outlook. That's it for me. You are dismissed whenever you're done asking any question you have. I'm gonna stop recording, but I'm staying here.